Good morning, guys. Going to talk about nuclear reactions, just the basics about them. Um, the reason I always say good morning to you guys is because I like to work in the morning, so like that's when I do all of my work and recordings and stuff. But you could be like, good afternoon, I don't know. All right, so nuclear reactions, I found this cool rainbow PowerPoint for it, which is cool because it reminds me of the visible spectrum of light. In order for us to really get to what a nuclear reaction is, we have to get some background information on a couple of things. One of those is radiation. And I would like you to write down some notes for this because you're going to be taking a picture and putting it into your Google Doc assignment. So for radiation, what I would like you to write down as the definition is wave energy. Wave energy. So anytime that energy is moving as a wave, we call it radiation. The most, I guess, like accessible type of radiation that we think about all the time is light. Light is only this little tiny section here of the electromagnetic spectrum, the light that we see, but all of these other things are also considered light. So X-rays, gamma rays, radio waves, those are all waves as well, and they're considered light waves. They interact with the electromagnetic field around us, which is everywhere, and then depending on how they interact with that field, at what wavelength, they do different things. So like visible light, we can see. Infrared light, we feel as thermal energy, as heat. Microwaves are used, of course, in like your microwave to wiggle around all the particles in your food so that they have friction with each other and heat up. Um, and then, of course, radio waves, we use those to transmit sound. So, like, we send waves in the form of radio waves, and then your radio picks it up and turns it back into sound, which leads me to this other picture here. This is actually a seismic wave. So, earthquakes are made by seismic waves. That's a type of sound wave moving through a medium, and sound is another type of radiation. Up here, I have the symbol for like dangerous nuclear radiation right here. And that's a type of radiation. And then there's also one other type of radiation called particle radiation. And so you could have alpha radiation, beta, or neutron radiation. Sometimes radiation is dangerous, but only if it's ionizing. Ionizing means that it's going to knock electrons off of whatever it's touching. And when it does that, it destroys like the atomic structure. So like if you get radiation, it's literally like taking the electrons off of your atoms that are in your body, and then they can't do what they're supposed to be doing. So you can die from radiation. Um, Ultraviolet radiation is another type of ionizing radiation, X-rays, gamma rays, and so those can be dangerous. Pretty much these other types, they don't have enough energy to knock off electrons, and their wavelength is too big, so we don't have to worry about them in terms of danger. So radiation, wave energy, and remember I would write down some example types of that. I would write down nuclear radiation because that's going to be one of our topics in this class. There's, of course, waves that are in light, electromagnetic radiation, sound radiation, okay, and then there's also particle radiation. All right, let's go to the next page of background information. Okay, I know that there's a lot of times in life where you've learned about what the atom looks like, and me too. And if you look up an atom, you get a bunch of pictures that are like this. Unfortunately, those are like all super wrong ways to depict the atom. The reason we do that, the reason we make it like this is because that way our little brains can understand it. So atoms are actually like pretty complicated, so we reduce them down to this model because it's way easier for us to understand. If you recall, there's three parts of an atom, so there's three subatomic particles. The proton is the positively charged one. I would write this down if I were you. Okay, so if you really have it memorized, like you 100% for sure know that protons are positive, like you don't have to write it down, but a lot of students think they know and then they actually don't. So I would suggest doing it. So the proton is positively charged. It defines the atom. So if you have one proton, you have hydrogen. If you have two protons, you have helium. If you have three, you have lithium. If you have four, you have beryllium. So every atomic number on the periodic table indicates how many protons are in that atom. So if you discovered a new atom, or you thought you did, and it had 76 protons, you would go to the periodic table, find element 76, and learn it's already been discovered. Okay, electrons. Electrons are the negatively charged particle. I remember that because the capital E has three negative signs on it, right here, and right here. So it's electrons negative charged. Those are really important for chemical bonding. And they also can make ions. When an atom has a different number of electrons than protons, it becomes an ion, which means that it's charged. It has a slightly positive or negative charge. If you change the number of protons, you change the element altogether. And then neutrons have no charge. I remember that because it spells no, like you could spell no charge, neutral. Neutrons are there basically to help hold the nucleus together. And if you change the number of neutrons, you get what's called an isotope. So some carbon has 6 protons, 6 neutrons, and 6 electrons. But you could also get a carbon isotope like carbon 14, and then it has a different number of protons or a different number of neutrons than protons. Okay, so this is not really what an atom looks like. Here's what you need to remember about an atom. There is a nucleus. It's unimaginably small. We call the things in the nucleus the nucleons, so that would be the protons and the neutrons. And it's really unimaginably small, like you can't really think about it. It's so small. And then there's this relatively huge electron cloud that goes around it, and that's where the electrons are flying around. But they fly around in these really weird patterns, and you can't really tell exactly where they are because they're like moving so fast all the time. So when we draw them like this in this picture, that's not really accurate because they could be anywhere in the space. And then most of the atom is not even anything. So most of it is just empty space. So you have a teeny tiny little nucleus, we have the electrons flying around, but most of the atom is actually empty space. So those are like the three things to remember about an atom. Okay, reactions involving the atom. So remember how I said you can change the number of the number of the neutrons or the number of the electrons? Well, if you're dealing with the electrons changing, you're dealing with bonds, chemical bonding. And that would be like what you would study in a chemistry class. You put different things together, like if you have an oxygen and 2 hydrogens, they can share electrons, and that makes water. So that's a different chemical than just oxygen and hydrogen by themselves. They behave differently, they do different stuff. So chemical reactions that you do in a lab, to like see what's going to happen or that your teacher's making you do, those are all going to be about changing the configuration of the electrons in different atoms. If we start involving the neutrons, then we're going to start getting the things that are called nuclear reactions. Nuclear decay, or it can also be called radioactive decay, fission, and fusion. We're not really going to talk about this one too much in this class because I'm going to talk about that more in a different class that you guys are going to have to take, but we're going to really focus on fission and fusion right now. Okay, so the definition of fusion, definitely write this down, is the combination of two lighter elements into a heavier element. Why are we saying lighter and heavier here? Well, it has to do with the number of particles in the nucleus. So if we're taking more and more neutrons and protons and we're putting them together into a nucleus, then that actually like literally gets heavier. So that's why we say heavier. So we're going to take, and I know this is confusing because it says deuterium and tritium, and these are two forms of the same element. So these are both forms of hydrogen. But hydrogen can either have 1 neutron in its nucleus or it can have 2 neutrons in its nucleus. Well, when a deuterium, which is a type of hydrogen, hits another type of hydrogen called tritium, they can actually fuse together. So they get stuck together and become one nucleus. That nucleus then, instead of just having 1 proton in it, has 2, and that's why we say it is helium. It's heavier now. The other thing that happens, though, is that this particle radiation in the form of a neutron gets released, and this has a lot, like a crazy amount of energy. So you remember E equals mc squared, matter and energy are really the same thing, but when you change forms, Okay, when you change matter into energy, it makes a lot of energy. The other type is fission. So fission is when you take a heavier element and you break it down into two smaller ones. So this example is showing you uranium-235, and the reason I know it's 235 is because of this number right here. Okay, uranium-235, and it's getting whacked in just the right way with this extra particle that's flying around. And when that happens, it's going to release a lot of energy along with two elements that are not as heavy as uranium. And in this case, it's barium and krypton. So that's what those stand for right there. So fission is when you're splitting something apart. Okay, fusion is when you're putting something together. And we in this class really have to focus on fusion because that's what our two topics are. Okay, how do we get all of this energy on the Earth? Well, we get it because at the core of the sun, of our main sequence star, there is nuclear fusion happening. Mostly it's hydrogens being fused into heliums, but it'll continue going on and there will be even more elements produced in our sun. There are some right now, but it's mostly hydrogen and helium. Like counting the other ones is like kind of pointless at this point because our star is so relatively young. The other thing that's really important about fusion happening is that in these main sequence stars, okay, we get all the elements made up until element 26, iron. And then once these things start to die, we can have what's called a supernova explosion. And this is actually a cloud of gas that's left over from a supernova. If you took a picture of a supernova, it would just be the flash of light. They happen often, but they're kind of hard to see from Earth because we can't see very many stars from here. But we do have them every once in a while. We haven't had one really visible from Earth in a while, so maybe we'll have one soon. It'll be really exciting. Even in the day, you're supposed to be able to see the flash of light. It's so bright. So I'm crossing my fingers that I get to see a supernova in my lifetime. But this is the cloud of gas that's left over. And in this cloud of gas after a supernova, there was the ability, because of the amount of pressure and crazy heat that happens during the star explosion, that we get all of the other elements on the periodic table, except for the ones that we can only make in a lab that only exist for a second. But most everything gets made in stars. So the Big Bang made our hydrogen and our helium and a little bit of our lithium. But everything else is going to be coming together in the life cycle of a star. So remember, in a main sequence star, we have this gas that is hydrogen and helium from the Big Bang. It gets all sucked together, and then it starts fusing on the inside once it gets enough pressure and temperature, once it's hot enough. And then it starts whacking all of those hydrogens together into helium, and then those will start whacking into bigger elements until you get to iron. Then you get a huge explosion in the case of a supergiant star. Okay, and then you're going to have all the other elements. So that's really important to us about fusion. Fusion of all the elements that are in this beautiful universe, except for the ones that are man-made, which you can look up, are done in the life cycle of stars. Bye, guys!